repairing the body, actually reducing biological age, is likely to be a lot easier than slowing aging down. If we get to this a whole year of extension of life from starting in middle age, then we are going to have a full-blown, full-scale war on aging.
Welcome to the Siim podcast. Our guest today is Dr. Aubrey de Grey. Aubrey is one of the world's leading gerontologists. He is spearheading foundations that seek to extend human lifespan. In this episode, we talk about his predictions regarding the longevity escape velocity, which is a concept where medical science has reached a point you'll be able to outpace aging. Aubrey, welcome to the show.
Well, thank you for having me.
Yeah, I'm super excited and honored to have you on the show. I've read a lot of your books, and I'm also a huge, a fan of the idea of the longevity escape velocity. And coincidentally, it's actually been like 20 years since you published the first paper on this topic, or where you coined the term. So it's kind of 2 decades have passed. So what are your, let's say we can begin with, like, you can maybe explain it a little bit what you wrote 20 years ago, and maybe how has your opinion about this changed, 20 years later?
Sure, yeah. Okay, so the idea of longevity escape velocity, which, as you say, I first talked about in 2004, arose from the big idea I had 4 years earlier, which was that repairing the body, actually reducing biological age, is likely to be a lot easier than slowing aging down. In other words, slowing down the rate at which biological age increases. And that has, of course, dominated and defined my scientific research ever since. It's remarkable how well the plan that I put forward back then, which was first published in 2002, has stood the test of time. I have not had any requirement to, expand my original list of 7 deadly things, as I called them. And, that means that it's quite likely that nobody will ever have to expand that list, and that once we can develop ways to actually do the damage repair in each of those cases, we will be in a very good position. So how does longevity escape velocity arise from all of that? Well, it is a consequence of the fact that rejuvenation, reducing of biological age, buys time. The slowing down of biological aging is better than nothing. But if you're already in middle age when one starts to do that, then one doesn't actually gain very much. Eventually one gets sick anyway. Whereas if you take someone who's, let's say, 60 or 70 and you restore them to being biologically 40 or something, then, it's going to be another 20 years before they get to be biologically 60 again. And that's time that people like me can spend improving the therapies. The reason one would not take someone age 60 or 70 back to biologically 20 is because the initial damage repair portfolio is not going to be 100% comprehensive. We are going to be able to fix some things more easily than others, but there's going to be some easy damage we can fix, some difficult damage we can't fix. And what's going to happen, therefore, is that, when the person comes in aged biologically 60 for the second time, when they're 80 or whatever, they're actually not really going to be biologically 60, because all the damage that makes them biologically 60 is going to be difficult damage that the therapies don't work on, which means that however often and thoroughly we apply these therapies, the person's still going to get older, biologically older, which is not the idea, right? So the point is that in those 20 years, we will have improved the comprehensive of the rejuvenation, which means that those same people, even though they're full of difficult damage, can be re-rejuvenated, so that, because we've shifted some of the difficult damage into the easy category, so to speak, and so they won't be biologically 60 for the third time until they're, let's say, chronologically 110, and so on. So the formal definition of longevity escape velocity is simply, it's the minimum rate at which the scientists need to be improving the comprehensiveness of these therapies in order to stay one step ahead of the problem for people who are getting the state-of-the-art therapies at any particular point. And we never have to get 100% perfect at repairing damage. We just have to approach 100% sufficiently fast. Furthermore, the rather heartening thing is that that rate at which we have to approach 100% slows down over time. This is not a case of, accelerating change like the singularity, because the more that we can fix, the less that we have left that we can't fix, the longer it's going to take for that ultra difficult damage to become abundant enough to cause us to get sick. So this means that once we reach longevity escape velocity for the first time, the hard part is definitely done. It's vanishingly unlikely that we will ever fall below longevity escape velocity after that. So a friend of mine back in about 2007, coined the term the Methuselarity by contrast with the singularity to define this one point. So you ask, the last part of your question was, how have my views changed? There's one thing that's changed a little bit in relation to all of this, and that is with regard to how soon we're going to reach longevity escape velocity. In particular, how much we are going to have to postpone the health problems of late life in order to be at the Methuselarity in the first place. Originally, I said I thought we would probably need 30 years, a 30-year increase, because 30 years is what we would need to be able to make enough improvements to get the next 30 years. But now I think I've reduced that number to about 20 years. That's simply because things are moving faster now. Biology, biomedical research is moving faster, and it's going to, very probably continue to move faster. So the threshold of the Methuselarity is easier than it used to be. Now, of course, if we look at actual timeframes, how soon we're going to reach the Methuselarity, then it's a much more difficult question because it's still some way off, and therefore, we can only speak in terms of probabilities, in terms of predictions, because unforeseen obstacles may occur. So I say that I think that we have a certain amount of chance of getting to a particular point with that chance. And specifically, I always talk about the 50% chance. I think we have a 50% chance as of now of getting to the Methuselarity within the next 12 to 15 years, so in the second half of the 2030s. And of course, that has slipped over time. 20 years ago, when I first started making such predictions, I said it would be about 25 years. And, it has slipped. However, the good news is that pretty much all of the slipping occurred in the first 10 years of those 20, essentially because research went a lot more slowly because it was so poorly funded. In the past 10 years, the second 10 years, things have been a lot better. A lot more money has been coming into the field, and things have duly started moving a lot faster. Now, I will say that the money that's come in, even though it is enormous compared to what was available beforehand, is very, very unevenly distributed. And that means that we still have a lot to do to make sure that, that money is not rate limiting. Nevertheless, we're getting there. There's more and more, things that are hard, things that are difficult and, hard to make money out of, that are increasingly being funded. So, I'm still pretty hopeful right now. The final thing I want to say in terms of what's changed over time is the reception to all of this. When I started out 20 odd years ago and I started talking about rejuvenation, everybody thought I was crazy. Virtually nobody understood in the field what I was even talking about, and I was accused of being unscientific and so on. It took best part of 10 years to fix that. To really, win the argument and get people to understand that this made sense. And the real, the real end of that period, the kind of definitive end, was the publication of the Hallmarks of Aging paper in 2013, which was basically a restatement of what I had said a decade earlier, but which was published in a top journal by people with lots of credentials, and therefore, was very much accepted. And that paper has become, by a huge distance, the most highly cited paper in the whole of the biology of aging this century, and it's very likely to stay there. But what hasn't happened, or certainly had not happened by that time, was a widespread acceptance of the concept of longevity escape velocity, which honestly shocked me, because the timeframes and the plausibility of getting to the methylarity, getting 20 years of extra life is very, very uncertain. And I was proposing quite a number of very ambitious research programs to get there. So I think it was reasonable to be skeptical about at least some of that. But once we get those 20 years, the whole concept of longevity escape velocity is inescapable. I mean, it's just high school maths, if that, right? So I was like completely shocked. But of course, the reason is the conclusion, which is that that a lot of people alive today have a good chance of living indefinitely. And, that sounds politically scary to a lot of people. So they run away very fast, irrespective of the logic. Now, even that is beginning to change now. A number of people are talking about longevity escape velocity correctly. A number of people, especially the people who did their undergraduate degrees in maths, which is a few biologists, are actually, talking about it as obvious and inevitable. And the media is picking up on it now in a manner that resembles what happened with rejuvenation. They're getting to be more respectful about it and talking about it as realistic, even if they still talk about it as speculation. So yeah, a lot has changed and all of it has changed in a positive manner.
Yeah. Yeah, that's quite interesting. So you're saying like that within this 12 to 15 years, we'll reach a point where, I guess like a simple way to put it is that with every passing year, your life expectancy will still increase by 1 year or even 2 years. So you're outpacing death with the advancements in this regenerative technologies and medicine.
Exactly that, yes. I mean,
Right.
though I do want to emphasize again, in case anyone missed it the first time, that I only think that we have a 50% chance of getting there within the next 12
Right.
years. I think there's
Yeah.
at least a 5% chance that we won't get there for 100 years if we hit a lot of problems. I always have to emphasize that.
Gotcha. And yeah, I mean, I agree that, over the last even like 4 years or so, the talk about longevity has become almost like mainstream, and a lot of people are interested in that. So I guess the question is that has then there been any like hints of more advancements in this science regarding anti-aging and longevity that we are more confident in saying that in 12 15 years we'll reach that point? Because correct me, sorry, I'll like correct if I'm wrong, but I think the longest life extension in mice was achieved even like 40 years ago, and there hasn't been like much breakthroughs in that since that time.
Yeah, right. So, I mean, of course, the only reason why my timeframes have been coming down as time has passed in the past 10 years, when they didn't really come down in the previous 10 years, is because of progress. I mean, that's my measure, because I'm at the coalface seeing all the things that are happening. Now, of course, you're absolutely right that right now we have not succeeded in extending lifespan in mice by any more than we could do with calorie restriction, 40 years ago or more. 40 years ago is actually about the right number to use, because that in the early 1980s was the first time that people tried to do calorie restriction on mice that were already in middle age at the time. And the most that has been achieved there is about 4 months of additional life on such mice. Now, that is really why I have specified a threshold, which I call robust mouse rejuvenation, for what we need to achieve doing damage repair. And that threshold is to achieve 3 times more of an effect size than what has been achieved thus far. So in other words, we still start with middle-aged mice that have roughly 1 year to live on average. That means they're 1.5 years old already. They normally live to about 2.5. And then we double that. We give them 2 years of life on average, maybe 2.5, 2.75 to the maximum for the maximum, the oldest mice. Now, that would be 3 times as much. 1 year is 3 times 4 months, right? So I believe that not only will that demonstrate to scientists that we are really, we've really got the hang of this, that damage repair is going to be much more effective than anything else, but also it will completely change the conversation in the wider world. It will really convince people that we have a handle on this now. So as you say, you can't measure progress by trend analysis of lifespan experiments, but yet then you couldn't do that with powered flight either. I mean, it didn't. If you asked someone in 1900 how long it would take in 1950 to cross the Atlantic, then they might look at how long it took in 1850 and 1800 and 1750. They would see that liners were getting progressively faster at a very slow rate, and they would have come up with a very wrong answer for how long it takes to get across the Atlantic in 1950. So that's how technology is. You have to actually know all about the details that have not yet come together in order to come up with a realistic answer. And honestly, it is utterly scandalous that top journals still insist on publishing completely vacuous papers doing trend analysis and, coming up with pessimistic answers for how soon anyone will live to 150, let alone 1,000.
Right. Yeah, it's, how long did it took from the first airplane for us to have like jet planes and space travel or, going to space? So it was like
that's
rather
another
short
important
time.
thing. That's another important thing, yes. The predictability of fundamental breakthroughs in terms of time frames is nil. We all talk about how, top physicists were saying that powered flight was impossible right up until it was done. But we must also remember that Leonardo da Vinci was designing, heavier than air flight 400 years previously, and he probably didn't think it was going to take that long to make it work. So you just can't do it. Whereas once the fundamental breakthrough has been made, incremental refinements of that breakthrough to, give better and better performance tend to be rather predictable, especially when, there is public demand for it, which is not going to be in short supply for this particular type of breakthrough.
Right. Yeah. So you mentioned that earlier that rather than focusing on slowing down the speed of aging, we would want to, regenerate the body. So would it be then that calorie restriction is an attempt to slow down aging and it's not, regenerating the body, which is why it hasn't yielded the very super impressive results?
That's right. And it's worse than that. Not only does calorie restriction, have a kind of brick wall that it hits, that brick wall is a lot sooner in longer-lived species. Longer-lived species get far less impact from calorie restriction than short-lived ones do.
Right.
And this is perfectly predictable from evolutionary theory. So it's not surprising, though it was terribly swept under the carpet for a long time. Now, of course, one thing we do have now that we didn't have 40 years ago or even 20 years ago is calorie restriction mimetics, drugs that make the body think that it's not getting enough food when it actually is. And these are handy because, of course, people like eating, and therefore, you can get, even though you don't get much out of calorie restriction, at least you can get maybe the same amount without having to actually starve yourself. However, the critical thing is you're never going to get more than what you get with calorie restriction itself because you're activating the same metabolic, reprioritization, so to speak. So, in fact, we care about this. And in our study, our big combination rejuvenation study that we've been doing since early last year, we did use rapamycin, which is the best calorie restriction mimetic right now, as one of our interventions, because we wanted to use it as a good baseline to compare with the various damage repair interventions that we were also putting in. And this has worked out rather well in the sense that rapamycin certainly has worked in our hands, same as it has worked in everyone else's hands. And we can look at, what the other treatments achieve in combination with it.
Right. So it just buys you more time to perhaps live.
It buys you more time, but also what's rather important is that there's always a debate about whether calorie restriction is a treatment or whether it is the natural state, and the ad lib feeding is the overeating, which is kind of shortening your lifespan. This is true in humans, and to be honest, it's also true in mice. Mice get fatter as they get older. So, it's a question. So basically what we're thinking that we'll do in subsequent rejuvenation, combo rejuvenation studies, is we're just going to give everyone rapamycin. We're not going to try and recapitulate something that people already know, namely that rapamycin works. We're just going to use that as the baseline on which we want to add more.
Gotcha. Right. So what is then, let's say, the invisible technology, the breakthrough that we would need to see for us to really make these big breakthroughs in lifespan and regeneration?
So the key thing about rejuvenation is that it's a divide and conquer approach. That, just like most complicated engineering, right? It's you've got to get a lot of different components working, all of them reasonably well, before you can put them together and get the overall desired result. And so, I've always had this 7-point plan, but we must be clear about what that plan actually means. Each of the 7 things is a category of damage, and there are many different examples within that category of, types of damage in different organs, for example. So the reason the classification is useful is because it pairs up with a list of 7 damage repair approaches, each of which is generic. In other words, it can be used against all examples within the category, though, of course, the details may be different. You need different types of stem cell for different organs, for example. However, there's a bunch of good news here. One is that there is now, in each of the 7 categories, a choice. We have multiple different options for how to achieve the damage repair in question, which we certainly did not have 20 years ago. And the second thing that's rather good is knock-on effects. If you repair one type of damage, then you make the body less stressed, and you have the effect of slowing down the accumulation of other types of damage, even if you're not actually targeting those other types directly. So that's probably going to be also rather important. So what we've achieved so far with our study that's which we call RMR1, the first combination rejuvenation treatment that anyone's ever done, is we've got definite contributions. The 2 sexes, we're obviously doing this with a lot of male mice and a lot of female mice. The 2 sexes are behaving rather differently, but so we'll pick apart the statistics when the study is over, which is going to be another few months yet. But it's obvious already from the kind of interim data, which of course I'm putting out on social media every month or two, that the that the impact is exactly what we were hoping to see. However, we definitely have not hit it out of the park. We're definitely not going to beat the record for what's been achieved in the past by all that much. We're certainly not going to get to the 1 year that I want to get to eventually. And what this tells us is we just are not hitting everything yet. We're not rejuvenating every aspect of damage. And so next time round, we're going to be using different interventions. And if we can pull enough money together, we're going to be doing more than 4 interventions, the 4 that we had this time. I would very much like to be doing 8. The design of the study allows this. We look at subsets of the interventions as ways to make proper comparisons, but we don't do all the subsets. We only do each intervention individually, and we do all but one. So that means that the size of the study only grows linearly with the number of interventions, not exponentially. So we really like to do one with like 8 interventions.
I want to take a quick break to let you know that you can now get my new book, The Longevity Leap, on Amazon. It contains 24 chapters ranging from the biology of aging to all the major chronic diseases such as heart disease, kidney disease, neurodegeneration, and I also cover over 70 clinically relevant biomarkers for chronic diseases and their optimal ranges. You can get the book from the link in the description. You mentioned that the aspect of damage, which is one characteristic of aging. So, and in the SENS Foundation, you've listed out like these 7 categories of cellular damage that happen because of aging. So maybe we can go through some of these and give a brief explanation of what it is and what is the kind of countermeasure against that aspect of damage.
Yeah, well, so obviously I've written and spoken a lot about this, so let's not be too thorough here. But I can certainly
just a brief explanation.
Yeah. So the one that I talk about as a kind of illustration most easily, because it's just the easiest to explain, is loss of cells. So loss of cells simply means cells dying and not being replaced by the division of other cells. And in some tissues, the cells just, they die and they are replaced by the division of other cells. And so there isn't an accumulation of damage in the form of diminishing cell number. But in some other tissues, that's not the case. And the example that's easiest to discuss is Parkinson's disease, which is pretty much entirely caused by the death and non-replacement of a particular type of brain cell called a dopaminergic neuron. These neurons are located in one very small part of the brain called the substantia nigra, and they make dopamine, which is a very important chemical in the brain. And when there's not so many of those cells, there's not so much dopamine, and you get Parkinson's disease. Everybody loses about a quarter of their dopaminergic neurons by old age, but the system is set up to tolerate that. It's not set up to tolerate losing like 3/4 of them, which is what some people do, and those are the people who have Parkinson's disease. So the natural, obvious approach to repairing that damage is stem cell therapy. You put cells into the substantia nigra or thereabouts that know what to do. They differentiate into the required cells, the dopaminergic neurons, and lo and behold, you got dopamine back, and your Parkinson's disease goes away. That's the theory. Now, in the 1980s, I think, no, 1990s, a group in Sweden had a go at this. They said, all right, let's try this. And they injected some stem cells into the brains of various Parkinson's patients. The problem was, where did they get the stem cells? Back then, we didn't have, the Yamanaka factors. We didn't have any real knowledge about how to manipulate stem cells. And so the only thing they could do was isolate stem cells from aborted fetuses. They got hold of a bunch of aborted fetuses, and they tried to extract cells from the developing brain. And, they did their best, but the substantia nigra is small, and the Anlagen, as it's called, the place where the stem cells are coming into existence, is very, very small. And so it was rather hit and miss. And sure enough, nearly all of the people that they injected had no benefit. No harm, but no benefit, because the cells were the wrong cells. They didn't differentiate into the right kind of neuron, so nothing happened. Right. But a few people got lucky. A few people got the right kind of cell, and the results were spectacular. There was actually, the group wrote a kind of retrospective case study a few years ago on I think it was the 25th anniversary of the treatment of the first person who actually responded. And basically the guy was, had proper Parkinson's, was getting the standard of care at the time, which is a precursor of dopamine called L-DOPA. Symptoms completely went away after one injection, such that they took him off L-DOPA, and still there were no symptoms for more than 10 years. Eventually, the injected dopaminergic neurons started to deteriorate, but, it took a very long time. So that's about as close to a cure as you can imagine. And now, of course, now that we have, far better understanding of how to manipulate stem cells in the laboratory before injecting them, it's a completely different world. And there are, I think, 5 clinical trials, either already in progress or about to start, trying to do exactly the same thing. And, everyone's very hopeful. So that's the kind of thing.
Interesting.
Now, of course, as I mentioned, there are multiple ways to do each of the types of damage repair. In the case of cell loss, the main thing that's come along very recently is something called partial reprogramming. So this is basically injection of these things called the Yamanaka factors into the body. The idea here is that the cells that we do have in the body that are still there may be less regenerative, less stem-like than they used to be, and that we'd like them to be. And these Yamanaka factors reverse that. They essentially turn back the developmental clock of cells just a little bit, so that they become more stem-like and more regenerative. And that has essentially the same effect as injecting bona fide new stem cells. Whether it would work for Parkinson's disease, not clear, because the cells are gone, but it should work in other cases where the stem cells are just less stem-like.
Gotcha. Right. So in the example of the longevity escape velocity, you would get injected with new stem cells every few years to keep them, I guess, that prevent from fading away?
Well, yes, but more than that. So yes, you'd get injected with new stem cells every decade or whatever. But the key thing about longevity escape velocity is that stem cell therapy for some organs or tissues is easier than it is for others. So let's carry on talking about the brain. A key feature that makes stem cell therapy for Parkinson's disease possible is that the cells that are needed that make dopamine are located in this very small part of the brain called the substantia nigra. You can just inject them into the right place. Whereas in, for example, Alzheimer's disease, eventually in the later stages of Alzheimer's disease, you've got other types of neurons dying all over the brain. And that's much harder to fix. You can obviously inject stem cell precursors into the brain, same as you can for Parkinson's disease. But the thing about the brain is it's not like the circulation. It's not like the bloodstream. There is a fluid that the cells are bathed in. It's called the cerebrospinal fluid, but it's viscous. It's very sticky, which means that when you stick stem cells into it, they just sit there. They don't move around and disperse all over the brain, which is what you'd need them to do. So we need a better trick for that. And there is one that has been worked on for the past decade or so by one group at Albert Einstein College of Medicine. It's essentially genetic engineering to make these neuronal precursors swim and actually actively disperse around the brain before they differentiate to become real neurons. The way one does this is by getting them to emulate the gene expression patterns of another type of brain cell called a microglial cell. It's a very clever idea, but it's a very exploratory stage right now. It's very much not ready for clinical trial. So I can see that as the kind of thing that we would do, after we had reached longevity escape velocity in order to stay.
Gotcha. Right. Will there be any method of, I guess, cloning or creating stem cells? Because right now they're getting them from these umbilical cords, right? Most of them. So is there a way to create stem cells in the lab that act like more potent or kind of smarter stem cells?
It's not so much the potency. So we can certainly make arbitrarily potent stem cells using the Yamanaka factors in the laboratory. In other words, the reason for isolating umbilical cells or cells from the amniotic fluid or from the placenta, those reasons are less pressing than they used to be, because we can make those cells now. Now, that's not necessarily the whole story because it takes time to make them and so on, but it's most of the story. However, one thing that is very important here is whether those stem cells have the genetic code of the person who's going to receive them. So if you take stem cells from somebody else and you inject them into you, then they're going to be rejected by the immune system, just like an organ transplant. The rejection may take a while because early stage powerful stem cells tend not to be very immunogenic, but they're immunogenic enough. They won't last long. And they may do good anyway in the near term before they get killed off by the immune system, but it's not ideal. So that's called an allogeneic stem cell transplant. But what one can do instead is start from the person who's going to receive the cells. You take cells from that person, you de-differentiate them, as it's called, using these factors. So you've got the right kinds of stem cells that you want, but they do have the genetic code of the recipient. And then you inject them back and there's no immune reaction. That's called an autologous stem cell transplant. And the pros and cons here. Autologous is far better because the cells last, but it's also far more expensive and difficult to do because you need to do it. You need to do it one-off for each patient, whereas the allogeneic ones can be off the shelf, so to speak.
Gotcha. Right. So we talked about cell loss and replacing them with stem cells. What about limbs and bones and those kind of things? Would it be if you maintain these healthy cells and rejuvenate the cells with the organ or the limbs, maintain quote unquote younger phenotype with the limbs, or would you also have to end up replacing limbs and organs and those kind of things?
Yeah. So honestly, it's hard to know at this point. I've always said, and it's still true, that at the first stage when we reach longevity escape velocity, sense 1.0, let's call it, the bits that are not working well yet, that are still clunky, will matter. and therefore we may very well require organ transplantation for some things. It may be either to grow a new organ in the laboratory and, transplant it rather than repairing the existing organ in situ. Now, that can't really be done for limbs because we don't know how to grow a limb. Though people are actually working on the idea of growing entire bodies without brains. That turns out to be genetically fairly straightforward. And using those as the transplant. But that's still a long, long way off. So really, we want to be looking at doing in situ rejuvenation of everything, including muscle and bone. And there's no particular reason why we shouldn't be able to do that. And for that matter, of course, the brain, which is an organ that, if we replace that all in one go, that would rather defeat the object. So, so yes, we've got to do these things. And, these things are all made of the same stuff as the rest of the body. They're made of cells, and cells are made of the same stuff, DNA and proteins and so on. So the same kinds of approaches should certainly work everywhere in the body.
Gotcha. Right. I guess we can move with some next type of damage, maybe the mitochondria. So that's also like one of the main theories of aging, the mitochondrial free radical theory of aging. So how does the mitochondria relate here?
So, the free radical theory of aging, of course, was first put forward in the 1950s, and it became the mitochondrial free radical theory of aging in the 1970s, when the same guy, Denham Harman, realized that mitochondrial mutations might matter. And in the 50s, Harman was one of a number of people who were thinking along the same lines. And if he'd been hit by a truck that day, someone else would have come up with the same theory 6 months later. In the case of the mitochondrial theory in the 1970s, that was very much not the case. He was way ahead of his time. In fact, that idea really didn't become mainstream for another 17 years after that. Nevertheless, we are here now. And yes, mitochondrial mutations accumulate during life, and there is good reason to believe that they matter. The specific pathologies that they contribute to, that's still a matter of debate. And indeed, the mechanism by which they accumulate and the mechanisms by which that accumulation is toxic are still pretty unclear. But the absolute worst thing to do would be to just wait and see, to spend our time just trying to understand and answer these questions and not actually try and do anything about the problem until we have these answers. That's the way that basic scientists think. They think they need to understand everything about something before they actually try to manipulate it. Whereas engineers like me, we think in terms of knowing enough, but not necessarily knowing everything. So what do we do about mitochondrial mutations? Well, the good news is that evolution has done most of the job for us. Mitochondria are these really, really complicated machines with well over 1,000 proteins in them, and all but 13 of those proteins are actually imported into the mitochondrion naturally. They are, they're synthesized in the body of the cell, the cytosol, and there is a system for importing them. So theoretically, we could kind of piggyback on that system, on that machinery, by putting copies of the mitochondrial protein coding genes into the nucleus along with all the others, and modifying them so that they are substrates for that mitochondrial protein import machinery. This idea was first put forward in the 1980s, and it was made to work for one protein in one organism, namely yeast. Then it hit a whole bunch of brick walls and everyone gave up, and I kind of revived that whole area in the late 90s, early 2000s. We at my previous foundation have worked tirelessly on that idea, and we've made huge progress, but it's still not there. And I honestly don't know whether it ever will. I don't know whether we will be able to actually make this work. It's called allotopic expression. So I've always been on the lookout for ways to achieve the same results without allotopic expression. And essentially the way that one would try to do that is by selective pressure, essentially to cause the mutant mitochondria to lose out in the natural selection process that goes on within each cell between mutants and non-mutants. And there are various ways to do that people have thought of, a couple that I've thought of, but none of them have really got anywhere until now. We now have a few ideas for how we might be able to do that. Essentially, because we understand more closely the machinery of mitochondrial recycling and biogenesis. I would have to get very technical in order to go into the details, but this is another case where we have more than one alternative approach to addressing the problem than what we had 20 years ago.
Gotcha. What about the elimination of these worn out mitochondria that accumulate during aging?
Well, that's what it would be, you see, because mitochondria, even in non-dividing cells, they're constantly dividing. Some of them are being destroyed, and other ones are dividing to replace the ones that were destroyed. So that's why we have the opportunity of, well, we have the phenomenon of natural selection. Once there is any mutant mitochondrial DNA, you've got genetically different populations that are competing with each other. And the idea is to bias that competition.
Gotcha. Right. But one of the types of damage, one of the 7 ones, is intracellular waste products and extracellular waste products. So 2 of them. Can you explain?
Yeah, sure. So first of all, let's talk about extracellular waste. So the most well-known example of this is amyloid beta. This is the main constituent of CNL plaques in Alzheimer's disease. For quite a long time, people have been interested in using the immune system to get rid of this stuff, essentially causing the immune system of the brain to engulf these this waste product, because it's actually not very hard to break down once it's inside the cell, and so that's kind of enough. But people have had only limited success there, and in particular, even though now we can actually make that work, it doesn't have much impact on Alzheimer's disease pathology, largely because Alzheimer's is a complicated disease that has a lot of other things going wrong at the same time as the accumulation of this plant material. However, the same idea can also be used elsewhere in the body. In the later stages of diabetes, you have an accumulation of something that looks a bit like CNL plaques, but it's actually made of a different protein. And so we might be able to do the same thing. Then in the heart, there's something called transthyretin, which accumulates in this way. And this turns out to be really important in extremely old people. It was first discovered maybe 10 or 15 years ago in supercentenarians, people who are over the age of 110. And actually, I funded an entire project that's now been spun out of the company to try to get rid of this stuff. The approach that we took was a bit different from the engulfing that I just mentioned. In this case, what we're looking at is actually proteolysis, chopping the stuff up in situ. And this is done with a special kind of antibody called a catibody. So that's for extracellular junk. For intracellular junk, stuff that accumulates inside the cell, you've got a slightly different story. First of all, most of the examples of this happen in the lysosome, which is kind of the incinerator of the cell, the garbage disposal machinery of last resort. And the reason stuff accumulates there is because even though the lysosome is very, very good at breaking things down, there are some things that it can't break down. So this is the main cause of blindness in the elderly. We get this thing called macular degeneration, which is driven by the accumulation of a byproduct of vitamin A that the cell doesn't know how to break down. Way back, 25 years ago, I had the bright idea of using bacterial enzymes for this, because bacteria are extraordinarily versatile. You can find bacteria to break down more or less anything. And this is used in environmental decontamination to get rid of, explosives in disused airfields and things like that. Anyway, it turns out to work. It turns out you can find bacteria that can break down the stuff that accumulates in macular degeneration. Now, of course, we would not want to inject those bacteria into the eye. That would be bad for you for various reasons. But what we can do is some genetic analysis. We can find out what genes they have that allow them to break down the material. And then we just do gene therapy, which it turns out is a lot easier in the eye than it is anywhere else. And so this is something that we pursued for quite a while in my foundation, and then we spun it out as a startup company, and that company has progressed it further, and it's now about to be sold to Big Pharma. It's going pretty well. So, that's the big success story of that idea. Right. Same kind of thing has happened with atherosclerosis, the number one killer in the Western world, of course. That's driven by a similar process. In this case, the waste product is not a derivative of vitamin A, it's a derivative of cholesterol. cholesterol itself, people get a bad rap, but it's a very essential molecule. But it gets spontaneously oxidized sometimes, and some of those products are indigestible. And again, so this has been addressed. In fact, the way in which that's been addressed most powerfully so far is not by breaking it down, but by extracting it, essentially finding a way to get it out of the body. And again, that's an equivalent approach.
Interesting. Right. So there will be like this. I think one concept is like this xenocatabolism, or is it like related to this?
Xenocatabolism is a word I invented for exactly what I said earlier, using bacterial or fungal enzymes to break down things that the human body can't do because the human genome doesn't have genes encoding enzymes that work.
And in the future, you'll be able to like do it with like a pill, theoretically, or something.
Probably not, to be honest. I think this will always be a gene therapy thing. This will always be a case where we need to actually have ourselves create a protein that they can't normally create. Now, the other approach that I just mentioned for cholesterol, where you're extracting it rather than breaking it down, that absolutely could be done, without gene therapy. But in that case, again, we do need to inject. So the way in which that's being approached, again, by a spin out from my previous foundation, is using a molecule called cyclodextrin, which is a well-known molecule used for lots of things in medicine. And my group discovered a clever way to modify cyclodextrin so that it was specific to oxidized cholesterol and would preferentially extract that even without, depleting the overall amount of cholesterol in the body, overall amount of normal cholesterol, which is the main problem why you can't use high doses of statins, because statins alter they inhibit the synthesis of regular cholesterol.
Gotcha. Right. How far is gene therapy then right now? Like, you hear some rich people injecting them with gene therapy, but is there any evidence that it actually works as of now?
Well, yeah. I mean, at the moment, there are lots of clinical trials going on with gene therapy. Now, I mentioned a moment ago that the eye is a particularly easy place to do gene therapy. That's simply because of immunogenicity. The eye basically doesn't have an immune system at all. And therefore, you don't have an immune reaction when you inject foreign stuff, which you do have if you do it in the rest of the body. There are ways around the immunogenicity of gene therapies, but they are at an earlier stage, which is why there are very few clinical trials so far outside of the eye. But in the eye, there are lots. Because it's not just about aging here. We've got lots of congenital diseases that you can address using gene therapy. And so that's being done, yes.
Gotcha. Yeah, you hear like muscle growth gene therapy and different kind of this clotho-protein gene therapy, etc. So it might take more time to see if it works.
That's right. And of course, what we've got now is early adopters having a go at this, even though these things are not approved in the Western world yet. The famous such person is undoubtedly my great friend Liz Parrish, who got into the field kind of sideways. She was first interested in type 1 diabetes, the autoimmune disease, because her son has that. But somehow or other, she had the presence of mind to come to one of my conferences about, 11 years ago. And the rest is history, so to speak. She's been extraordinarily valuable in the field. And she got that way basically by giving herself a platform. And she got that a media platform to be speaking on stage and on camera a lot, which she's fantastic at. And she got that way by being what she calls patient zero, by using herself gene therapy in Latin America somewhere for telomerase and follistatin, which follistatin is a protein that enhances muscle quality and growth. And as you say, clotho is the next one on the list, so to speak.
Right, gotcha. Yeah, super interesting. What's going to happen with that? Next we can briefly just mention some of like division obsessed cells and death resistant cells that are on the list.
Yeah. Well, so let's do death resistant cells first, because of course there's been huge progress there. That's a term that I coined to be a bit more general than a term that was already around and is still very popular, called senescent cells. The cells, for various reasons, get into this aberrant state where they are either not doing what they were supposed to do or not doing it as well as they could. But in addition, they're actively toxic. The toxicity aspect was only recognized maybe 25 years ago. It was first put forward by a fantastic researcher who tragically died earlier this year named Judy Campisi, who was actually also the first person, really the only senior person in the whole of the biology of aging who immediately understood what I was saying about rejuvenation back in 2000. Anyway, yeah, so you got to get rid of these cells. And the immune system knows this, and it does its best to get rid of them. But some of them just resist the immune system in rather the same way that cancer cells resist the immune system. And so we have to find ways around that. And people have been trying all manner of things, and there are already a number of small molecules, including ones that are in clinical trials now, which selectively kill off these cells. The thing is, the selectivity isn't all that good yet. It doesn't really work all that well. But people are grinding away, making it better and better. And we're getting really quite good senolytics now, as they're called, drugs that do this. Another approach is to enhance the ability of the immune system to detect and destroy these cells. And again, there's quite a bit of progress in that area, which is no surprise, again, because of the comparison with cancer. As you know, we've got huge advances in cancer immunotherapy over the past decade or two, especially the past decade, and that's continuing. So that's all great. And then, of course, there is cancer itself, which is the other cell, having too many cells strand of sense. And yeah, I mean, cancer immunotherapy, has made huge strides way back when I started running conferences more than 20 years ago. Every single conference, I would have one or two people who were experts in cancer immunotherapy. But it was it was a bit tragic, really. There was no progress. And then suddenly, 10 or 15 years ago, there were these two huge breakthroughs, the discovery of CAR-T and the discovery of checkpoint inhibitors, which suddenly made immunotherapy for cancer work. I mean, not universally. It works mostly best on blood cancers like leukemias and lymphomas. But, people have obviously been improving it and refining it, and it's getting to the point of being able to work against solid tumors now as well. And there's more and more progress there. Then there is the approach that I put forward against cancer, which was to abrogate telomere elongation. And this was always by far the most ambitious and most speculative aspect of sense. There were definitely people who said that they bought everything else I was saying about damage repair, but there's no way we would get this telomere control thing to work. But that has become a lot better now as well, because there's now something that I like to call Wilt 2.0, the second generation of the idea I had, in which we now have a way to kill off cells that are expressing a lot of this telomere elongation enzyme telomerase, not just by stopping the enzyme from working, which would only slow down, which would only cause progressive telomere shortening, and therefore would be a very slow way to kill a cancer. Now, there are ways to essentially turn telomerase into a suicide gene. In other words, you give the drug, and if a cell is making telomerase, it incorporates the drug into the telomere, and that kills the cell very quickly. I could go into the mechanics of that, but basically, yeah, it's fantastic. And that is now also in clinical trials, being led by a great company named Maya Biotechnology. They spoke at my conference in Dublin last year. So the video of that talk is online. But I very much encourage people who want to know more about that either to look that company up or to write to me.
Gotcha. Right. But is the telomeres does it also have beneficial effects for lengthening telomeres on healthy cells, or how does that differentiate?
So there has been a lot of oversimplification over the years of the pros and cons of telomere length. For sure, you don't want your telomeres to be too short. And indeed, the study that we've been doing, RMR1, over the past year and a half, one of the 4 interventions that we are including is gene therapy for telomerase to extend telomeres. Even though mice normally have really long telomeres, and they make a lot of telomerase naturally. It turns out that putting even more in is helpful because mice are so spectacularly bad at maintaining their DNA, especially their telomere DNA. Um, so yes, there are definitely benefits, but the question is, how much benefit would there be in the body as in the human body? And the answer is, well, there might be an impact on the immune system if we mess up telomerase. If we completely, if we didn't have a telomerase gene in the immune system. But most other places, it looks like there probably won't be a problem because, first of all, cells, most of our cell types just don't divide. Either they really don't divide at all, like neurons, or they divide so rarely that they don't exhibit significant telomere shortening, even in a whole normal lifetime. And then on the other hand, the cells that do divide reasonably often, like the blood stem cells, for example, they need a bit of telomerase, but they make a bit of telomerase naturally, but only a little bit.
Right.
So cancers make tons of telomerase, which means that if you have this drug that makes telomerase into a suicide gene, it kills cancer cells really quickly. And it's easy to use the right kind of dosage, the right kind of duration of this drug, so that you have a minimal effect on blood stem cells or stem cells in the gut, for example. So that's fine. As for the immune system, the great thing there is that the telomerase expression is very closely regulated, so that cells only express, when they express telomerase, they do make quite a lot of it, but that's only during the very brief phase when the body is fighting off an infection. When that happens, of course, we have this thing called the adaptive immune system, where the infection is recognized by a teeny tiny minority, a very small fraction of 1% of our white blood cells. And those ones who recognize it are triggered to proliferate really fast. So we get a huge expansion, and that takes telomerase. But then, once the infection has been overcome, those cells mostly die off, and the ones that don't die off are just become quiescent and no longer dividing. So yes, you would not want to do this telomere, this telomerase killing thing while you have an infection, while you're suffering from malaria or whatever. But any other time, absolutely, you'd be fine.
Gotcha. Right. And the last is the extracellular matrix stiffening.
Yeah. So when the Hallmarks paper came out in 2013, I was very pleased because I realized, and I was right, that was the end of the battle I had been fighting for the previous decade. I would never again need to justify the whole damage repair approach to my colleagues. However, the fact is the Hallmarks paper was a bit mediocre in a number of ways. And one enormous way was they just left out stiffening. They just the word glycation does not appear in the entire paper. And there are a few other problems, like we were talking about intracellular and extracellular junk a moment ago. In the Hallmarks paper, it only talked about proteinaceous junk. It talked about loss of proteostasis. So I've just given you two examples: oxidized cholesterol and modified vitamin A, which are not proteins. Right, and they were just left out completely. Now, of course, the Hallmarks paper has been revised, both by the original authors and by other people in the past few years, and these omissions have been somewhat corrected. There's still a few problems, but it's better than it was by a long way. But yes, I mean, it was appalling that they left it out. I told them so, and they were embarrassed. But anyway, so stiffening is caused by a process called glycation, which is a spontaneous chemical reaction between the proteins that make up the extracellular matrix, this lattice that gives our body its biophysical properties, and sugar in the circulation. And these reactions are slow, and they are under control to some extent, but they still happen. And eventually you get these chemical bonds between proteins that are not supposed to be bonded together, and that causes this loss of elasticity. So the goal is to break up those bonds, to break those bonds. And luckily these bonds have a different chemical structure, very different chemical structure than anything that the body lays down on purpose. So it's not, out of the question to be able to do this. But it turns out to be really hard because these bonds are thermodynamically very stable. So if you find a small molecule that's a drug that's able to break them, it's going to be reactive and it's going to have side effects all over the shop. So that's pretty challenging. One way out of that is to use enzymes. And because enzymes have extraordinary specificity, right? So they can be reactive, they just won't react with the wrong thing. And that's the approach that people have been pursuing. We funded a group at Yale University for a number of years that made a huge breakthrough in that area, that was published in Science and led to the spinning out of a company named Revel Pharmaceuticals, R-E-V-E-L, that has, made further progress. So we're still a long way from the clinic there. Well, very long way, but big progress is being made.
Gotcha. Wow. Yeah, that's super interesting. According to the longevity escape velocity theory, then, we're going to make incremental progress in all of these different areas. And, right now they're all like pretty rudimentary, and we're getting better and better over the next, 5, 10, 15, 20 years.
Exactly that. Yes.
Gotcha. What would be like, is there anything that's going to happen within the next 5 years? Is there going to be, we're very close to some like more breakthroughs?
Well, I mean, we're not going to be at longevity escape velocity in 5 years. I'm pretty sure. But what will happen over this time is critical. First of all, we're going to get more and more things getting into clinical trials, including in offshore jurisdictions. I'm a particular fan of a place called Prospera, which is a special economic zone in Honduras, actually on an island called Roatan, and which is, focused very much on medical tourism, especially in relation to longevity. And, if all goes well, and they do have challenges, legal challenges, but they seem to be navigating those. If all goes well, then we are looking at, that place being the global hub of medical tourism in the next couple of years. And that will make a huge difference because early adopters will go there and avail themselves of treatments, and they will talk about the results. And, obviously we need the results to be positive, but as time goes on and more positive results happen, there will be FOMO. There will be fear of missing out in established jurisdictions. And this is what I believe is absolutely vital, absolutely indispensable for the modernization of regulatory structures in the US and elsewhere. At the moment, there's huge vested interest in the status quo. Nothing happens. It's very frustrating, but FOMO will do it. And the other thing that's going to happen in the next few years is the kind of work that we're doing, the work on mice. If we get, as and when we get to this threshold called robust mouse rejuvenation, a whole year of extension of life from starting in middle age, then, the conversation is going to be ridiculously different. We are going to have a full-blown, full-scale war on aging. Not like the war on cancer, which was, it was a great deal better than nothing, but it was only a trebling of the budget of the National Cancer Institute. It was imperceptible to the American public. We're going to have a proper war on aging. And that will change everything. And honestly, I will feel at that point my job is done. That the science will happen. There will be enough people. Everyone will be working on it. And of course, I'll continue to do my bit. But my main job will be done.
When is the mouse reversal expected to be published?
Well, so again, it's not close enough that I can put a firm time frame. It's still pioneering technology, but I do put a 50% probability. And at the moment, I'm saying 3 to 4 years from now.
Okay, gotcha. Right. With all of these things, they have obviously like risk. You mentioned these early adopters going to these faraway jurisdictions. So, like, I guess the kind of rational standpoint would be that if you're like older and closer to the average life expectancy, you would be more riskier. Whereas if you're like younger, like me, I'm 30, so I would maybe not be an early adopter. I would wait, for these things to kind of have more evidence.
Yeah, absolutely right. And of course, it's not your actual age that matters here; it's your biological age. So I'm 61, but you wouldn't know it to look at my numbers. I'm biologically probably in my 40s still. So again, I'm being more conservative than the average 61-year-old would be.
Right. Yeah, that's kind of important to think about. And what would, so right now, and that also depends on, okay, what you're going to do until the next 15 years to reach that, to make it, to make sure that you live until that. So those things, would you think, like, diet, exercise, some supplements, or what do you think should people do?
When people ask me what I do, I emphasize the avoidance of the risks of death that do exist now. So, I don't accept seminar invitations to dangerous countries.
Mm.
Things like that.
Bungee jumping.
Right, exactly. I've never seen why people would do those things. But yeah, I mean, as I said, calorie restriction doesn't really work doesn't really achieve very much in humans, and therefore calorie restriction mimetics don't either. When it comes to lifestyle and diet and so on, again, you can't really do much. I mean, of course, you can do something. You can avoid shortening your life, but essentially, over and above just living the way your mother told you to, and not smoking and not getting seriously overweight and having a reasonably varied diet, there's not a lot. And therefore, quality versus quantity comes into it. If you're sacrificing a lot of quality of life to do this or that thing, whether it's because this or that thing costs a lot of money that you don't have to go on vacations or whatever, that increases your stress level, and stress is bad for aging. So, at the moment, I would say, live a fulfilling life, really, is the most important thing. And, of course, I really always emphasize, do what you can to hasten the arrival of longevity escape velocity.
Right.
So, people like me, I'm doing a lot. Other scientists can do a lot by, getting into the most impactful areas of science. Wealthy people can help in the obvious way by accelerating the science financially. People like you are helping right now by, educating your audience. And the more of that happens, better. I always point out, advocacy, everyone can do advocacy. Everyone can talk to their friends, their family, their colleagues, and raise the quality of thinking and action in this area. Most people say, okay, I can't do anything, I don't have any money. And I always point out that the poorer you are, the more people who are wealthier than you. So,
just spreading the word about these ideas and the science is, I think, for the average person, the most they can do. But yeah, I mean, super excited to, like, for those future studies and the trials. Before I ask my last question, where can people learn more about your work? Where can they support the work or anything like that?
Well, of course, go to our website, levf.org. I imagine you'll put it in the show notes. But my foundation is named after the concept of longevity escape velocity. LEV is longevity escape velocity. F for foundation.org. And everything that we're doing is there. There's a whole bunch of information about why we're doing it and all that. And of course, there's a nice big friendly donate button.
Of course, yeah, we'll put the link in the show notes. And the last question is, what's this one piece of advice or habit that you wish you adopted sooner?
Well, I wish I had adopted sooner. Well, the honest answer is I'm probably too trusting. I have chosen to be rather naive about human nature.
Gotcha. Right. Yeah, that can be problematic sometimes. Well, thanks for coming to the show. I'm really thankful for sharing your knowledge, and looking forward to the future work.
Well, thank you for having me.
Yeah, I'll see you around.
Bye for now.
All right, that's it for this episode. Make sure you check out my new book, The Longevity Leap, on Amazon. I'd also appreciate if you share this episode with a friend or family member. Other than that, my name is Siim. Stay tuned for the next episode. Stay empowered.